that the condition, the second component satisfy automatically. But for the first component, when you plug in this, okay, so now you're gonna get the first term equal to this one multiplied by plus and minus one, and that have to be 0. So that imply what? This term have to be 0, right? If this term is not 0, so it cannot, this equation cannot be satisfied. So this end up with this condition, right? I just take the product here, so I end up with this equation. You can see that the second component of the traction is satisfied automatically, but the first one cannot be satisfied automatically. It can be satisfied if C3 make the term here is equal to 0. So this will give me this condition. So I end up with the value of C3. So C3 is not arbitrary. Okay, C3 have to satisfy that condition to make sure that the condition, the boundary condition at the left and at the right end are satisfied. Okay, now I get C3. Okay, is that clear to you? I need to check the natural boundary condition at the top and bottom surfaces as well, because I told you before, at the top and bottom surfaces, we know the mixed condition, right? We know traction equal to 0 in x1 direction, so I have to check that. For the condition in the x2 direction, we don't know yet, because we need to know the displacement before we can check that. So now I just simply check the traction boundary condition in x1 direction. So the first thing that I have to do, I have to form that boundary conditions, right? So this is the traction in terms of stress in x1 direction, right? So I get sigma 1, 1 multiplied by N1 plus sigma 1, 2 multiplied by N2. It have to be equal to T1, 0. And T1, 0 here is 0, right? And sigma 1, 1, sigma 1, 2 is 0. Sigma 1, 1 is simply the one that I showed you in the previous slide. Okay. You can see that. And because at the top and bottom surfaces, N1 is 0. So this is satisfied automatically. So you can see that the form that I gave there satisfy this condition automatically. Okay. If you take a look at the form that I gave, now I know C2, I know C3. C1 is still unknown, but we have the condition left to be satisfied, right? So the condition at the top and bottom surfaces in the condition in normal direction haven't been checked yet. Okay, I have to check it. But to check that, I need to get displacement field. This is the step that is quite difficult compared with the previous example, right? Because we need to know the displacement first. And you know that to get the displacement, you need to perform the integration. So this is unavoidable. Okay, we have to do it. Okay, so we can generate strain field from stress field that I got. And this is the summary of stress field that I got before. I plug in C2 and C3 that I got before. So this is final form of stress field that left in term of C1. Okay, C1 is still unknown. Okay. Now I use this strain relationship. I can get epsilon 1, 1. I plug in sigma 1, 1 and sigma 2 today got here. I plug it in here. So I get epsilon 1, 1 like this. The same thing, I can get epsilon 2, 2. I plug it in. So I get this. And epsilon 1, 2, it's clear that okay, the shear component, shear strain vanishes because shear stress vanishes as well. Okay. So this is the final strain field that I got. Okay, strain field that I got here still, expressed in terms of the unknown C1. We still have C1 there. So because we already checked equation, the compatibility condition for phi, so we don't worry about the existence of the displacement field. So we can always get the displacement field by performing the integration. So we have this relationship. Okay, so I have strain displacement relationships, and I know strain components already, right? I know epsilon 1, 1, epsilon 2, 2, and epsilon 1, 2 from the previous slide. So I set that equal to the gradient of displacement. For example, epsilon1 is simply del u1 by del x1. Epsilon2 is simply del u2 by del x2, right? And epsilon1 is simply expressed in terms of the displacement gradient like this. So I have three equations here. I will not show you in detail because the process is similar to the one that I showed you for the example one. So I perform the integration, okay, of all three relations that I have above. Okay, you can follow the same procedure, but the detail may be different because the function that you have involved, you have to get involved here are different. Okay, that's just simply the detail of the calculations. The procedure should be the same. So once I perform the integration, I will get the displacement field like this. This is the final displacement field that I can get from the integration. Okay, I didn't say that okay, get these two displacement components. It's very, very simple. I didn't say that. Okay, it will take some time because you have to perform the integration. It's not that difficult, but it's quite long process, right? You have to perform the integration of all three equations there. Okay, and finally you end up with this expression. You have three more constants in addition. When you perform the integration, you also generate A here as the unknown and B there as well and C there. Okay, all three that I got here came from the integration of all three equations that I have here. And all three here, as I told you before, they are responsible for rigid movement. Okay, A here represent rigid rotation about x3 axis. B represent the translation in x1 direction, and C represent the translation in x2 direction. And don't forget that we also have C1 sit there. C1 is still unknown as well. That came from the gauge feed. So now I am ready to take the boundary condition, the displacement boundary condition at the top and bottom surfaces, and we expect to get some of the constant that I have left here. Okay? Is that clear? So now I check the boundary condition on the top surface first. At the top surface, I need u2 equal to 0 at every point on the top surface. So at the top surface, I have to plug in x2 equal to a to b, right? And this may be wrong, I think. And I think this is wrong. Okay, maybe you have to help me to correct this. This should be b. Okay, it have to be b. And this should be b as well, I guess, right? Okay, everywhere I have to change it to b. Okay, I have to apologize. Okay, I just prepared a note this year for this problem, so help me correcting this. Okay, I plug in x2 equal to b, so I look at the top surface here. But x1 here can be any value from minus a to a because every point on the top surface, this condition have to be satisfied. So now I get what? I can conclude what? Because this condition have to be satisfied for every x1, every point x1 at the top surface. So the constant a here have to be 0, right? Because this equation can be satisfied for every x1. That imply that, and all the remaining term here are just simply constant. So a have to be 0, okay? And the remaining constant, the combination of the constant, the remaining constant, okay? Or I can say that the sum of all the term here have to be 0 too, right? So I will get these two conditions. Don't forget to change a to b, okay? Change a here to b, okay? So now I get two conditions. At least I know that a have to be 0. So we cannot have the rigid rotation. It should be clear because if we don't allow any point at the top surface to move in x2 direction, so you cannot have rigid rotation. Okay, so and the second condition here cannot tell us anything about the constant C1 and C2. We just say that okay, this combination have to be 0. Okay, I have the condition left at the bottom surface. I do exactly the same way. I set the condition at point there. The U2 have to be 0. Again, change A here to B. Okay, this should be minus B, not minus A. Okay, because A and B are different. Okay, so change A to B. So now again, this condition have to be satisfied for every x1. So I think this is wrong too. I just switched A and B. This have to be A, okay, and this have to be A, right? The same here. So this it should be A, right? Because x1 range from minus A to A. Sorry for the confusion here. So change A to B, change B to A. Okay. So since this condition have to be satisfied for every x1 for minus A to A, so that implies that A have to be 0 again. So we end up with the same conclusion for A. Okay, A have to be 0. And also the remaining constant that I have there have to be 0 too, right? Okay, so I come up with the second condition. So now you can see that the first condition, the equation star there, and the second equation, double star, that I marked by sub double star here. So the two equations here can be used to solve for C1 and C, because you can see that there are two equations and two unknowns. So we can solve that two equation. So finally we can get C1 and C. Okay, so we solve linear equations here. So we end up with C equal to 0 and C1 equal to this. Okay, now we're done. So you can see that the gas fee that I have before satisfy all the condition, and I also get some constant. Okay, but if you look at everything carefully, it still remains the constant B that you cannot get it from here, right? If you go back to look at the displacement field U1, you can see that you have B left there, and B cannot be obtained from any condition of this problem, because if you look at this problem physically, because you don't have any less strain against the movement of the body in x1 direction at the top and bottom surfaces. So this body can slide in x1 direction. So you can say that the body here can experience rigid body motion, rigid translation in x1 direction. So that consistent with the constant B that you cannot determine from the condition that we have here, right? So B, the constant B cannot be determined. Or you can say that the displacement is non-unique for this problem. So this is a summary. Okay, I can say that the gas area straight function is the right one, with C1, C2, and C3. Taking this value. So if you take C1, C2, C3 equal to this, okay, the area straight function that I get there is the correct one, because it's the one that generate all field that satisfy all condition on the battery, and also the function itself here satisfy the compatibility condition, right? The value of C2 here just confirm that area straight function that I showed there satisfy the compatibility condition. C1 and C3 just came from satisfying the boundary condition, right? Okay, so now based on the values of C1, C2, and C3 that I got here, and also A and C, now I can generate the field like this. I plug it in, you can see that now straight field is known, right? There's no constant left here, okay? The same for strain. So I can say that strain and strain are unique. So that confirm the theory that I showed you before, right? The strain and displacement, strain and stress, once they exist, they are unique, okay? But the displacement for this problem, I got something like this. I plug in everything, C1, C2, C3, I got there. I found that U2 is identically zero, or zero everywhere. Or I can say that the material point inside the body here cannot move in x2 direction. It's just simply move in x1. And we have one constant left here, B, and that is the one that we cannot obtain from this problem, because the displacement B, this displacement in x1 direction is still not unique, right? B here represent the translation that can happen in x1 direction. Okay, this is the final result that I got. Do you have any question about anything here? We done with this problem, and I think I show enough examples for you for solving problem using inward technique for Airy straight function scheme. Okay, so I will give you one problem in the final exam like this. Okay, I will ask you to solve one particular problem, one particular 2D problem, and you have to follow the same procedure like this. I am not sure about the type of the problem that I ask you. It may involve the mixed boundary conditions, or it may involve big body force field. Okay, so last time I got the complaint that okay, I never showed, you know, the example in the class that I have non-zero body force field, but I asked that in the exam. But actually, if you take a look at the problem carefully, I think that there's no difference. If we have B equal to 0 or B not equal to 0, the only thing that different is just the detail calculations. All the steps are exactly the same. Okay, so I can change the information, the boundary conditions or loading conditions. Those can be changed, and you cannot expect to see exactly the same problem as what you saw in the homework, because I can always change the data set. You know what I mean, right? But the procedure cannot be changed. So the process that I show you in the example here can be applied to solve problems. Okay. Do you have any question about anything here? I'm done with 2D problems in x1 and x2 coordinate system. The remaining materials here in the note, I will not give you any exam problem in this topic. Okay, I just give you this as the extra material. Okay, and I may not have enough time to show you problem. So I don't have enough time to solve the problem in this case. If you would like to know more about this, you can read from the books, or you can take the second course with me. Okay, so I will talk about the 2D problems again, but in different coordinate system. Before we try to solve the problem based on Cartesian coordinate system, right? We use x1, x2 as the reference coordinates, right? But here I will change that setting a little bit. Okay, so instead of using x1 and x2 as the reference coordinates, here, so I will introduce a new coordinate system. I call the polar coordinate system, and this polar coordinate system shouldn't be new to you, right? You should be familiar with this in calculus. Okay, or I am not sure that Dr. Thirapong also mentioned about this type of coordinate system in the first part. Basically, the polar coordinate system is simply the special case of cylindrical coordinate system for 3D. Okay, if you look at cylindrical coordinate system that you have r, theta, and z, this is just simply the special case for 2D case. Okay, so I define the distance r. Let's look at point in the body. let X here is the point in the body. Okay, you can describe the location of the point using the Cartesian coordinate system, right? Using the coordinate like x1 and x2 that are sufficient to explain about the location of point X. But you can use the other type of coordinates to describe the location of X. Okay, we can use R. R is simply the distance from the origin O to the point X. Okay, if I define R like this, and also I define the angle theta. So theta here is simply the angle between x1 and the line connecting point O and X. Okay, with these two coordinates, it completely describes the location of X. Okay, X can be described by x1 and x2 or and theta. They are equivalent. Okay, so if you are given R and theta, now you can identify the point X in the space, in the plane, right? Okay, or I can say that the location of point X can be uniquely identified by R and theta. Okay, is that clear? Okay, and once I introduce these two coordinates here, I can also introduce unit vector in R direction and in theta direction. So I call the unit vector ER and E theta. ER here is, we call the radial unit vector. So it point in the direction parallel to the line connecting point O and X. Or you can think about this, the radial direction, right? And E theta here is the unit vector pointing in the tangential direction or the circumferential direction. Okay, if you draw a circle with the center at point O and with the radius R, that circle we have the tangent, tangent vector equal to E theta. Or you can say that E theta here is just simply the vector that tangent to the circle at that point. Okay, so we have two directions here. We can use these two unit vectors to form the vector in the plane. Okay, this is similar to the thing that you used before for x1 and x2 system, right? Because in x1 you can have e1, or you can use I, for example, unit vector. Here we can have e1 here. E1 here can be considered as what? The unit vector in x1 direction. That is a unit vector that we can use to explain any vector, right? And also e2 here. This is simply the basis for the vector based on x1 and x2 system. We can think about ER and E theta here as the basis. So we can explain, or we can express any vector in the plane in terms of the linear combination of E1, E2, or ER and E theta. Okay. Now, if we introduce the coordinates R and theta, or that we call polar coordinates, in this way, we can get the relationship between the two coordinates here and the coordinate x1 and x2 that you used before. Right? Because R and theta and x1 and x2 are used to represent the same thing, right? We use them to represent the location of a point in the plane. So we can construct the relationship like this, right? It should be clear to you. X1 here is simply R cosine theta. X2 equal to R sine theta, right? So you can take a look at the triangle. So you can form the triangle like this, the right triangle, right? So you can see that x1 is simply the length of that side, and x2 is that one, right? So now we can use the identity that you learned before. So x1 is simply this, x2 equal to that, right? Or in the opposite way, you can also write down R and theta in terms of x1 and x2 as well, right? R is simply the distance from the origin to the point X. So it's simply square root of x1 square plus x2 square, right? And the angle theta here is simply the arctangent function, right, of x2 over x1. So this is the relationship that are useful because we have the link between the two coordinates here and the two coordinates that we used before. Okay, they are not independent, I can say that. So r and theta and x1 and x2 are connected by this mapping. Okay, now you can think about the relationship that I show you here as the coordinate transformation. So you transform two coordinates x1 and x2 to r and theta, or vice versa. Okay, so now we can talk about the Jacobian of transformation. Okay, so x1 and x2 and r and theta are related like this. So in terms of the differential, dx1 and dx2 and dr and d theta can be related by the matrix that we call the Jacobian matrix. Okay, J is simply this. So this we call the Jacobian matrix of the transformation. I think that this kind of matrix is not new to you. You should learn this in calculus before. When you try to change the coordinates from one system to the other system, right? So we have the Jacobian matrix like this. And for this problem, for this particular case, x1 and x2 can be expressed explicitly in terms of r and theta like that. You plug it in here in the formula. Now you can come up with the explicit form of Jacobian matrix for polar coordinate system like this. Okay. I can also define the determinant of this matrix, and that we call the Jacobian of transformation. So the Jacobian of transformation is simply the determinant of the matrix here. And that is very important information that I will use later if I need it. Okay. Okay. We can also look at the relationship in the opposite way. So the first equation that I got here, we just simply express the differential of the coordinate x1 and x2 in terms of the differential of r and theta. We can do in the opposite way. We can express the differential of r and theta in terms of x1 and x2. And the matrix R here can be obtained by, you can think about the inverse of J, right? You can take the inverse of J and multiply both sides by the inverse of J. So now I can get R. So I is simply the J inverse, right? And I can prove that the inverse of J is equal to this. You have the matrix 2 by 2 here, right? The inverse of the matrix here can be obtained easily. So this is the final form of R. The matrix J and the matrix R are fundamental here. It just simply, tell you the relationship between the two coordinate systems. Okay. And J and R here can be obtained from the mapping. The mapping here tell you the relationship between x1, x2, and r and theta. Okay. Or you can think about this one, they are equivalent. And this mapping give you the information of J and R. Okay. And we will use that to perform the differentiation later, because don't forget that when you try to deal with the 2D problem, you deal with some operator. You deal with differentiation, and differentiation on operators are, carry out in x1 and x2 system. When you take derivative, with respect to x1 or x2, right? But now if you change the coordinate from x1 and x2 to r and theta, you have to be able to change or transfer derivative from x1 and x2 to r and theta. And J and R here will be useful if you want to do that. Okay. Also, before we talk about the operators, I talk about the field quantities first. You can think about the displacement. Let's say, okay, if you look in terms of x1 and x2, so if I look at the displacement at point x, So based on X1 and X2 system, so the displacement at point X can be component into, we can have U1 and U2, right? Okay, so we can think about the component of the vector in X1 and X2 direction. Okay, and this is the component of the displacement based on X1 and X2 system. At the same time, I can think about this displacement in and theta system. I can also represent this vector in this with the component in that direction and that direction, right? And they're gonna be equivalent. But I didn't say that the component have to be the same. We can have UR here. UR represent the component of the displacement, the same displacement, but the component that I look at here is the component in radial direction. And I can have U theta here. So the same vector, but we have different sets of component depending on the coordinate system that you are interested in. Okay, UR and U theta here, and U1 and U2 represent the same displacement at point X, but in two different coordinate systems. Okay, so now my question is, how can we transform from one to the other? Because you know that, okay, U1 and U2 and UR and U theta represent the same vector. We need to have some way to transform the components here from one to the other, right? And you learned that from Ajahn Thirapong, I guess, right? You know how to transform the vector and the tensor, okay, right? From one system to the other system. Okay, we use exactly the same rule here. Okay, the law of coordinate transformation that you learned before can be applied here. Okay, so now if I look at any vector in the 2D case or 2D vectors, we have this kind of transformation. So let's say that F here is a vector, have two components. F1 and F2 are simply component of vector F in X1 and X2 system. And Fi and F theta here represent the components of the vector F, the same vector, but in and theta system. The two set of components can be interchanged using the matrix A that I call transformation matrix. And this is for 2D problem or 2D case. So A is simply 2 by 2 matrix. You know how to get A, right? So you learn this from Ajahn Thirapong for the general 3D case. So this is just simply the special case. You have the transformation from one system to the other system like this. This is exactly what you learn from the third part. Okay, and I gave you the matrix A for this system because the polar coordinate system that I have there, I define in the way that I just mentioned. So A is simply cosine theta minus sine theta, and cosine theta. A here is not constant. It depends on the angle theta. So if you move from point to point and the angle theta change, let's say that you move not in the radial direction. If you move along the radial direction, A is constant, right? Because if theta is fixed, A is fixed too. But if you change the position X to any point, that theta change, so A change. Okay. So now I can transform. I can say that, okay, whenever I know the component of the vector in and theta system, I can transform it back to the components in X1 and X2 system using the transformation rule here. Okay, I can do in the opposite way as well. So let's say that if I am given the component in X1 and X2 system, I can transform back to and theta system as well. I just simply use the transport of A as the transformation matrix. Okay, I take A that I show you here and take the transport and multiply by F1 and F2. So that will will give me the component in AND theta system. So this transformation apply for any vector in 2D. So if you talk about the displacement is a vector, right? So I can transform the displacement like this from one system to the other system. Okay, I can change U1, U2 to U and U theta. At the same time, I can change U1, U2 to U and U theta using this coordinate transformation rule. Okay, body force, I can do exactly the same way. Traction, I can do exactly in the same way. Okay. Is that clear to you? How about the second order tensor? Let S here is the second order tensor. And I show the components here in 2D in terms of the matrix 2 by 2. Okay, let's say that is the components of the tensor in X1 and X2 system. And that is a component of the tensor S, the same tensor in AND theta system. Now, if I want to convert from one system to the other system, I want to convert the components in one system to the other system, I can use this relationship. This will give you the components in X1 and X2 system once you know the component in AND theta. And also I can do in opposite way. So the rule of transformation that you saw here is not new to you, right? You learned this from Ajahn Thirapong as well. And A here is the same matrix that I showed you before. Okay, it's a transformation matrix. Okay. Now the rule that I show you apply for stress and strain. Okay, because stress and strain are second order tensors. Okay, now I know how to switch from one system to the other system in terms of the field quantities. I can change the component of the field quantities from one system to the other system. Okay, I will be back in 5 minutes. Okay, please look at this, and also I will talk about the equation later. Okay, how can we transform the equation in one system to the other system in the same way as what we did here? Okay, I will be back just a moment. Okay. Okay. Let's look at the derivatives of the function and also some differential operators that we have to get involved into the problems. Okay. First, we need to be able to compute the partial derivatives of a function in an zeta system. Okay, we know how to do that in x1 and x2, right? Let's say that, okay, I give you a function. I want to get the derivative of that function with respect to r and theta. How can I do that? So this is the relationship that allow you to switch the partial derivative with respect to x1, x2 to the derivative with respect to r and theta. Okay, so how can I get this? The dot that I put there represent any function. So if you have a function f, you want to take derivative with respect to x1 and x2, you plug in f there, okay, and f there. So now you can convert the derivative from x1 x2 system to r and theta system using this transformation. How can I get this relationship? I simply use the chain rule of differentiation. Okay, so we know that r and theta and x1 and x2 are related to the, x1 and x2 are related to r and theta by the mapping that I showed you before. So now I can say that a function f, that a function of x1 and x2 can be changed to a function of r and theta using that mapping. Okay, so if you take a look at the matrix here carefully, the one that I show you here is simply the transport of matrix R that I show you in the previous slide, right? Okay, so this one is not new to us, right? It's simply the transport of the matrix R. So I gave you the matrix R already, right? Okay, this is the matrix R that I talk about. For the polar coordinate system, the matrix R here is explicit like this. Okay, so now when you plug this thing in here, you can change derivative with respect to x1, x2 to the derivative with respect to r and theta. Or what I can conclude here, the equation that you saw before that involve derivatives of function quantities with respect to x1 and x2 can always be interchanged to derivative with respect to r and theta using the rule here. Okay. How about the operators? If you talk about the gradient of a scalar function, okay, you remember, right? You learned this with Ajahn Thirapong before. Okay, let's say that f here is a scalar function. If you want to take the gradient of the vector, the gradient of a scalar function in x1, x2 system can be obtained easily, right? Can you remember what is the gradient of f in x1 and x2 system? Can you tell me the expression, the gradient of f, if you express in terms of coordinate x1, x2, you're gonna get something like this. You're gonna get derivative with respect to x1, right? Del f by del x1 and multiply by what? E1, right? Right? So this is the first component in x1 direction. So E1 here is simply unit normal vector in x1. And we have the second component as well. So you take derivative of f with respect to x2 and multiply by unit vector, right? In x2 direction. So that called E2. Okay, E1 and E2 here are simply unit vector. Okay. So that is the gradient of a function, of a scalar function in x1 and x2 system. Now this can be switched to that one. How can we do that? We just simply use the rule of differential that I showed you before, and also E and E theta here, and E1 and E2 are related by the angle theta, right? So based on that information, I can finally get the gradient of a scalar function f like this. Okay, I will not show you how to derive this. I show you the final expression here in case that if you are interested in computing the gradient of a scalar function, or if your governing equation involves the gradient of some quantities, if you want to work out the problem in an theta system, so you have to think about the gradient in this way. Okay. We also have the divergence of a vector. Let's say that we have a vector f. If we want to perform, we want to get the divergence of a vector f. So we have the expression here as well. Okay, that is the expression for the divergence of a vector f. Fr and f theta that appear there is simply the component of a vector f in R and theta system. Okay, if you think about divergence of a vector f in x1 and x2 system, the final form is simpler than this one, because divergence in x1 and x2 system is simply what? Derivative of f1, right, with respect to x1, right, plus derivative of f2 with respect to x2. That is the divergence of f. Oh, sorry, I have a problem with the mouse again. Like this. Okay, and f1 and f2 are components of a vector f in x1 and x2 system. So this is the form of the divergence of a vector f expressed in x1 and x2 system. And this one is a little bit more complicated. If you have to deal with the divergence of vector in an theta system, you have to use this formula. And the one that we will get involved later is the Laplace operator, right? Because if you remember, when we try to solve 2D problem using Airy state function technique, you need to check compatibility condition, and you have to be able to compute the Laplace of phi twice, and also the Laplace of Laplace of v as well. So the Laplace operator have to be computed. In an theta system, the Laplace operator is a little bit more complicated than the one that you saw in x1 and x2 system. This is the Laplace operator of, this is the Laplace of any scalar function f. You can think about phi, plug in phi there. So if you want to compute Laplace of phi in x1 and x2 system, it's quite simple, because you just simply take derivative with respect to x1 twice, and take derivative of the same function with respect to x2 twice, and you sum them. Now you get the Laplace of f in x1 and x2 system. But in an theta system, it's more complicated. So this is the explicit expression. So if you want to get Laplace of f in an theta system, you take the derivative with respect to theta twice and multiply by 1 over r squared, plus derivative with respect to r multiplied by 1 over r, and plus second derivative of f with respect to r twice, right? Okay, that is the final expression. Okay. Now take a look at the equation, because you talk about the operator. I talk about the operator here. You know about the operators in an theta system. You know about derivative in an theta system, right? We can interchange derivatives that we have in the equation with respect to x1, x2 to an theta system using the transformation rule that I show you here. So now we are ready to talk about equations, the field equations that we deal with before. For example, the equilibrium equations. For 2D problem, we have two different equilibrium equations, right? One is the equilibrium in x1 direction, and one is the equilibrium in x2 direction. That we have sigma 1, 1, plus sigma 1, 2, 2 plus b1 equal to 0, or sigma 1, 2, 1, 1 plus sigma 2, 2, 2 plus b2 equal to 0. We have two equations like that. Now we can convert that into two equations as well in ion theta system. This is the final expression of equilibrium equation in ion theta system. What do you think? It's a little bit more complicated, right? And you can see that the quantities that appear in the equation here are not in terms of sigma 1 1, sigma 1 2, and sigma 2 2 anymore, right? It's involved the component in ion theta system. So how can we come up with these equations? We just simply use coordinate transformation. We transform all components of stress and body force field into the component in ion theta system. And also we interchange derivative with respect to x1 and x2 to ion theta. Okay. Once we do two steps here, we finally end up with the equilibrium equation like this. We still have two equations, but the form are different. And the meaning of each equation is this. This is simply the equilibrium of force in R direction. This is simply the equilibrium of force in tangential direction. Or you talk about equilibrium in two different directions compared with the one that you saw in x1 and x2 system, because sigma alpha beta comma beta plus b alpha equal to 0, that we talk about the equilibrium in x1 and x2 directions. But it's equivalent to talk about the equilibrium in two different directions like this as well. Okay, the form look a little bit more complicated, but for some problems, solving these two equations may be simpler than solving in x1 x2 system if you want to know about this. So you can explore more in the books or in more advanced classes. Okay. Next, look at strain displacement relations. Okay, we have three equations, right? That's what we have for ion theta system. For x1 and x2 system, you have epsilon 1 1 equal to del u1 by del x1, epsilon 2 2 equal to del u2 by del x2, epsilon 1 2 equal to 1/2 del u1 by del x2 plus del u2 by del x1. That three equations that we have in x1 and x2 system can be converted to ion theta system, and this is the final expression that we have. Okay, we have relation for epsilon r epsilon r theta, and epsilon theta theta in terms of the displacement component in ion theta direction, like this. Okay, stress and strain relations we can have like this. If you take a look at the expression here, it's exactly the same as what we have before for x1 and x2 system, except that okay, you replace epsilon r by epsilon 1 1, epsilon theta epsilon 2 2 by epsilon theta theta, epsilon 1 2 and 2 1 by epsilon r theta theta r, right? And the same for stress. The form of the equation are exactly the same. The reason that the form doesn't change because what? Can you tell me? Because stress and strain relation that we talk about here involve no derivatives, right? It's just simply linear equation. So the form will not change due to the coordinate transformation. The form is still the same because no derivative are involved here. It's not the same as the one that you saw above because that involves derivative. So you have to change derivative with respect to x1 and x2 to ion theta system. Okay, is that clear? How about the compatibility condition for the 2D case? We have one equation, right? If you remember. Okay, so we have as well here. It's a little bit longer than the one that you have before, right? So this is the compatibility condition in ion theta system. Okay. We have enough components here, right? We have field equations, we have field quantities expressed in ion theta system. So now we should be able to formulate the boundary value problem of 2D case, okay, in Arn theta system. This is just the example that I show you here. So I can formulate the Bari-Baloch problem in terms of the displacement field, in terms of stress field, is whatever you like. Okay, this is the one that I should to show you how to formulate the problem in Arn theta system. I look at the formulation in terms of all unknowns. Okay, so I want to find the displacement field U Arn U theta, strain field epsilon r epsilon r theta, and epsilon theta theta, and straight field sigma r sigma r theta, and sigma theta theta. So I would like to get all these unknowns in Arn theta system that satisfy equilibrium equation, strain displacement relationship, stress strain relationship, and all these equations have to be satisfied at every point x in the body. And also we need to have the Bari condition. Again, the Bari condition have to be expressed in terms of quantities in Arn theta system. So we can have the traction condition and we can have displacement Bari conditions. And you can see that the form here are similar to what we have before in X1, X2 system, except that again, all the component of stress and displacement, normal vector, and the prescribed traction and prescribed displacement, all of them are expressed in terms of Arn theta, right? All components are referring to, Arn theta coordinate system. Okay, this is the final formulation. You can see that the number of unknowns, number of equations that we have to deal with here are exactly the same as what we have in X1 and X2 system. The number of unknowns, number of equations, number of conditions do not change, right here. So the only thing that changes is the detail, the form of the equations, and the quantities, the components that you have to deal with now are in Arn theta system. The form may look more complicated, but for some problem, this formulation can be solved easier than the formulation in X1 and X2. You know what I mean, right? For some particular problem, this formulation may be easier in terms of the solution procedure. Okay. Now, if we want to solve this problem using Airy straight function technique, what can we do? We can do exactly the same way, except that we work out the problem in Arn theta system. So the body force field that we used to represent in X1, X2 system, now we can represent in Arn theta. Remember, I talked about the gradient. This is the gradient of a scalar function V. So the form here is exactly the same for X1 and X2 because the form like this is coordinate independent. Once you express this form in Arn theta system, the form will be like this. If you express in terms of X1, X2 system, you're going to get B1 equal to negative derivative of V with respect to X1 and negative of derivative with respect to X2 like that, right? Oh, sorry, this one is wrong. So this have to be B theta, not B2. Please correct this, okay? And V here is simply potential function. But now the potential function is defined as a function of Arn theta, not X1, X2 anymore. Also, we have the representation of stress field. Once equilibrium equation is satisfied, or once the stress field that we talk about here is in equilibrium, now we can represent stress like this. So the representation here is similar to what you saw before for sigma 1, 1, sigma 2, 2, and sigma 1, 2, except that we now express in terms of Arn theta system. We don't have sigma 1, 1, sigma 2, 2, and sigma 1, 2 anymore. We just convert that into sigma r, sigma theta, theta, and sigma r theta. And derivative respect to x1, x2, we convert that to derivative respect to Arn theta. So finally, we come up with this formula. Okay, the idea is still the same. And we know that this condition is satisfied. Once you generate stress in this form, you can satisfy equilibrium identically. And phi here is Airy straight function. Defined in iron theta system is a function of iron theta instead of x1 and x2. Okay, so we have the same kind of representation, except that the detail of derivative may be different. Okay, because of the coordinate system that we use here. Strain field can be generated easily. Okay, this is a strain field that we can get. Once you get strain field from above, you can plug it in here. Now you can get strain field, right? And strain field that we got here is compatible if, can you remember? For the function phi that you have here, you can generate strain field. And then you can plug it in here, you can generate strain field. The strain field that we got here is compatible if the function phi here satisfy what? That equation again. This equation is coordinate independent because we derive that without, okay, the expression of the operator. So this operator can be carried out in x1, x2 system or in iron theta system. So I show you how to get the Laplace operator in x1, x2, and I also show you the expression for the Laplace in iron theta system, right? So this equation in iron theta system, when you expand it, look like this. It's quite long, right? And complicated. But actually, it's not that very difficult if you take a look at that carefully. Okay, term on the left-hand side, this is the Laplace of phi. Now you take one more Laplace here. Okay, so term on the right-hand side, this is the Laplace of phi. Okay, I show you the Laplace operator in iron theta system before. Now, if you want to verify that phi satisfy this condition, you plug it in here. Plug in phi there and plug in v there. If the two sides here are identical, now you can say that the function phi generates a strain that's compatible. Okay, is that clear? Now, once this equation is satisfied, now we can talk about displacement. Okay, now we can generate displacement because strain is compatible. Once strain is compatible, now we can compute displacement from this relationship. Or I can say that we can perform the integration of the tree here and follow the same procedure. Integrating this kind of relationship is a little bit more difficult for the second one and for the third one. But for the first one, it's simple. Okay, for the second one, it's a little bit more complicated because you have the other term that involved there. Okay, so you plug in strain that you got before, now you perform the integration, you can get the displacement field. Once you get all the fields, now you can check boundary conditions, right? It depends on the type of the problem that you focus on. If you have natural boundary conditions, now you can just simply generate strain field and check the boundary conditions. But if you have the mixed condition or the displacement boundary condition, you need to get displacement first before you can check the boundary conditions. Okay, this is the boundary condition that I talk about. There are two types. If you involve only the traction boundary condition, so you need only strain field to check or verify the boundary conditions. But if you have the mixed condition or you have the displacement based conditions, you need the displacement. Okay, that's gonna be more complicated. It's similar to the second problem I just showed you. Okay. Now, how can we come up with phi? That is the most important thing to do for this particular technique. There are several ways that I told you before. But if you prefer to use the simple technique that we call the inward technique that work for very simple problem, let's say that, okay, the problem in your hand is very simple. You would like to apply inward technique. Now you have to guess the function phi, right? The procedure will be exactly the same as what you used before for x1, x2 system. The only thing that different is the calculations, equation that you have to deal with. The number of equation is the same. but the form of equation may be different. Okay, that's the only thing that's different. So in terms of the calculations. Okay, I will stop here. I don't have enough time to show you any examples. Okay, to be fair to you as well, I will not give any exam problem related to the 2D problem in polar coordinate system. I just give you the outline here in case that you guys would like to extend your knowledge in this direction. You have enough background to study everything by yourself, or if you want to to continue taking courses that in this area, that is one option you can do. Okay, I hope that the material that I gave you in this class is useful and provide you the the basic background that you can apply to your research in the future. Okay, do you have any question about anything here? I'm done with my part. Okay, so I have 5 lectures, if you remember, starting from the formulation of the problem, work and energy principle. I talk about the solution, uniqueness, and the procedure for getting solution. I talk about Saint-Vernon problems and talk about special class of problem in 2D elasticity. Okay, so I hope that all the material that I cover here is enough, at least providing you the basic background in solid mechanics. Okay, do you have any question about anything for the final exam? I scheduled the final exam already, right, in next week, right, on Thursday 2nd, okay, from 9 to 12, right? Okay, so the exam gonna be the open book exam, so similar to the quiz. Okay, you are allowed to bring anything. Okay, and we're gonna have the online exam. The exam setting should be the same. Okay, you have to to turn on your camera and prepare things similar in a similar way. Okay, and the materials that I will ask you in the exam, it should cover all the material that I mentioned in the class. Okay, only the part that I mentioned in the class. Okay, so basically I can give you 3 or 4 problems. Okay, and I will show you the problem statement on the screen and ask you to solve the problem. And once you're done with the problem, you have to submit it in my course view. So if you guys are still not familiar with how to submit how to submit your solution, practice. Okay, so take a picture, convert into PDF, and combine into a single file and name the file. Okay, you should be able to do that in 2 or 3 minutes. Okay, do you have any question about anything? Okay, your friend said that, okay, you have the exam on 3rd December, right? But we schedule the exam on 2nd, so there shouldn't be any conflict, right? Okay, because I think I scheduled the exam before that class, right? Okay, so I still fixed the date of the exam on 2nd. There shouldn't be no problem because it's different day, right? So we still have the exam on 2nd December. Okay, from 9 to 12. Okay. Anything else? Also, I post the solution for the 2nd assignment because last night I grade that homework assignment. Okay, I found that, okay, all of you cannot solve that problem correctly for the 2nd assignment. So I post the solution for that case only for the 2nd assignment. If you have time, you can take a look. Okay, so and think about, you know, the way that you did and the one that I show you there. So there are some key difference that you have to be careful. Okay. Do you have any question about anything, including the quiz that we have before? Any specific question you can ask here? มีคำถามอะไรไหมครับถามได้เลยนะเราจะไม่มีเวลาเจอกันแล้วเนาะเราจะเจอกันทีก็คือวันสอบเลยวันที่2เนาะ Do you have any question about anything? No? Okay. You supposed to enter the exam room, okay, or in Zoom 10 or 15 minutes before 9 a.m. Okay, so I will post the link in my course view in the same way as before. Okay. Do you have any specific question about the exam or มีใครมีคำถามอะไรไหม Okay, if you have any questions regarding the exam material that you cover in class, about the assignment, okay, the quiz, any question that coming up before the exam, you can always line me, okay, or even we can have the group meeting, okay, if you cannot understand anything and you would like to set up the short meeting with me, that is fine too. We can discuss about things. Let's say that, okay, you and your friends, a small group that would like to discuss about anything, we can set up the meeting via Zoom or live call, whatever. Okay, because sometimes it's not effective, right? To, you know, to type and you ask me the question by typing, and I have to answer the, you know, your question may not be very effective there. So calling or meeting by discussing, okay, via Zoom may be appropriate, or even for the live call. Okay.